The free body diagram we came up with was that of the ladder, and the person standing on it with 180 pounds, 3 feet from the wall. We said on Friday that we're including the friction pad with the ladder here, so there was a normal force between the ground and that point of contact. This was not a surface in contact with a surface, but a point in contact with a surface, so we know where the normal force is. And we would expect that if this ladder were to start to slide, that this point A would be moving to the right, so the friction force should oppose that motion and point to the left. That was our reactions at A. At B, we had 1 point in contact with the wall. We had a normal force there, NB, that was pushing, the wall pushing on the ladder. And according to the prompt, the wall at B was smooth. So smooth means that the coefficient of friction is 0, which in turn means we can ignore a force of friction between those surfaces or that point in that surface. So they told us to ignore friction at B. We have a normal force but no friction. You can have a normal force without friction, but you can't have a frictional force without a normal force, at least in terms of if we have Coulomb friction. So here we have a normal and a friction. Here we have just a normal force. This was our complete free body diagram for the ladder. We're presuming that we're in equilibrium, and because we're saying what is the least amount of friction we can have, or frictional coefficient of friction we can have, before it's on the verge of motion. So we are in equilibrium here. We can sum forces in the x and get that NB minus FRA is 0. Sum forces in the y. We get the weight of the person plus the normal force at A, making the normal force at A 180 pounds. If we take a moment, I'll take it around A since it's acting kind of like a pin. I have 2 unknown forces there. I'll have 180 times 2 from the weight of the person minus 8.7 NB. For equilibrium, then, the normal force at B is 41.6 pounds, which means that the friction force at A is also 41.6 pounds. You should be checking in these friction problems at this step or once you apply motion equations. Friction forces must be positive, normal forces must be positive. If any of them are negative, first check your math to make sure you didn't make an error there. If you're still getting negative, that means that the way you drew it was incorrect. You have to flip the drawing and then change the equations to reflect the change in the free body diagram. It's different than with a pin. If you guessed the wrong sign, it didn't matter. It just meant your assumption was the opposite. Here we see it'll have a much bigger influence if you have any negative values for normal forces or friction forces. We have NA, we have NB, we have FRA. But what we needed to find here was the minimum the coefficient of friction needed to be so that we were, under these circumstances, in static equilibrium. None of our equations yet have this, have the mu. So how do we find the minimum mu can be for this to be in static equilibrium? Right. In this case, we have only 2 surfaces that will have friction between them. So when we're on the verge of sliding is where we are analyzing this problem. We're not saying that the mu has to be equal to this in this situation if we were just looking at it, someone climbing a ladder. All we're saying in this analysis is that the coefficient of friction must be at least this much because he's not moving even when it's just on the verge of sliding, but we're not sure if he's on the verge of sliding or not even close to the verge of sliding. We're analyzing this kind of worst case scenario here. So assuming he's on the verge of sliding, what would that mu value be? Well, that means that 41.6 will be this mu times 180 pounds. For him to be in static equilibrium, the coefficient of friction must be at minimum 0.231.